4, and after that, finally, after popping the label, the traffic can forward to the router 4. As you saw, the function of the RSVP in the RSVPT is two important things. The first, reservation of the bandwidth, such as the RSVP in quality of service integrated service model, and also for example, giving a label from the next top router and finally forwarding the packet, the data with that label. Let me to show you this process, but now you can you know the process, only we need to verify this process. You know that in this scenario, for example, we can capture all of this link for better understanding, and also we need to configure one interface tunnel. I configure all of the requirement in the router 1, router 2, router 3, 4, and 5. Only we need to configure the tunnel 0. But before then, let me to capture the link between R1 to R2. It's so important to understanding these details. Start Wireshark. This is the first link, the link between the router 1 and router 2. Okay, let me to capture also router 2. This is the capture of router 2, and after that this. Okay, this is the capture of router 2, and after that we can capture the link between router 3 and router 4. I'm going to show you only RSVP message. Because of that, we need to filter RSVP message in the Wireshark. And finally, we have another link, the link between router 4 and router 5. That's it. Okay, let me to start the configuration, but before the configuration, we can use only RSVP message. This is RSVP message in this capture. The next capture, RSVP. We don't have RSVP now. And then RSVP, okay. And finally, in the last link, RSVP. Now, we can configure the interface tunnel in the router 1. This is the CLI of the router 1. You know how we can configure the tunnel. It's so easy. conf-t interface tunnel 0. Okay. The first command is IP unnumbered loopback 0. We don't have RSVP message. Tunnel destination is the 192.168.254.5. Again, we don't have RSVP message. Tunnel mode MPLS traffic engineering. That's it. Okay, look at here. Now we don't have RSVP message. And then tunnel MPLS traffic engineering bandwidth requirement is 1000. It's okay. Then tunnel MPLS, for example, traffic engineering. For example, pass option 1. Okay, pass option 1 dynamic. This is the important command, because with this command, we say that IGPU should find the pass with the requirement of the bandwidth of 1000. After finding the pass, the RSVP should start its work. Look at here, pass option 1 dynamic. Now we can see some RSVP message. Let me to wait some second. After receiving the first RSVP reserve message, we can examine and we can compare the RSVP message that we have with the, for example, RSVP that I wrote before. Here in the router 1, tunnel MPLS traffic engineering pass option dynamic can show us now. We are using the dynamic method. Do show MPLS traffic engineering tunnels can show us that the tunnel now has the down state. Okay, we need to find some to wait some second. Again, do show MPLS traffic engineering tunnels. Okay, as you can see here, the tunnel operational status is down. Okay, after that, again check. Look at here, the operational status until now is down. After the operational status changed to up, we can examine the result of the captures. Okay, look at here. Now in the capture, we have only RSVP pass message. Also here, RSVP pass message and reserve message. Okay, very good. And now the tunnel is working. Yes, the tunnel status changed to the up. The reason that we experience some delay because of the IGP convergence and also RSVP function in this iOS. Okay, very good. Now we have a tunnel with the operational status of up. Show MPLS traffic engineering tunnels. Look at here. The tunnel status is up. Very good. Let me to check the status of the RSVP message. We can stop the captures because it's sufficient for us, and also the third capture. This is the third capture, and this is the fourth capture. The second capture, this is second capture. Very good. Starting from the capture of the link between router 1 and router 2, this is the capture, okay? Here the capture of the link between router 1 and router 2. Let me to compare only one RSVP pass and also another RSVP reserve. From 190 to 168.2541 to 2545, it's okay. RSVP is a protocol with a protocol number of 46. And after that, this is the RSVP pass message. Here we have some information, explicit route or ERO. This is the ERO. If you want, you can see the detail. Here we have this ERO 10122, 10233, 10344, 10455, and then 192.168.2545. This is the result of the IGP CSPF calculation. Okay. After that, about the sender specification, sender tunnel specification, we have this value. We need this amount of bandwidth as I wrote here. And after that, we have a label request here. This is the label request. That's it. And also we have another information. Now I'm not going to talk about them. And also we receive one RSVP reserve message from 10122, the router 2 to router 1. This is the, for example, link local message. After that, in this message, the RSVP reserve message, we can see that we have the flow specification with the amount of bandwidth we required, and also we have one label. The label is 200, and this is the label we received from the router 2. It's okay. Now we can see all of this information. Let me to show you the link, the capture of the link between the router 2 and router 3 here. We can see in the RSVP pass message that the source IP is from 190 to 168.2541 to destination of 190 to 168.2545. Here, as you can see, we received the one label. The label, we sent the label request, and also as you can see, the ERO changed to 10233, 10344, 10455, and finally 190 to 168.2545. Okay, and also about this tunnel specification, we don't have any change. Okay, here we can see insert, but this is not related about the insert because RSVP traditionally working for insert, we can see here the insert, but this is the RSVP with T extension. After that, in the RSVP reserve message, you can see that we received the label 300 from the router 3. It's okay. And after that, other information are same. Let me check the link between the router 3 and router 4. This is the link between the router 3 and router 4, and let me to find one RSVP pass message. This RSVP pass message, ERO changed to 10344, 10455, 190 to 168.2545. Also we have label request. Also we have, for example, session attribute, and also the sender tunnel specification or tunnel requirement. It's okay. And this is the RSVP reserve message for this tunnel. As you can see here, we are receiving the label 401. It's okay. And also flow specification. Very good. And finally, the link between the router 4 and router 5. This is the capture of the link between router 4 and router 5. In the RSVP pass message, it's the RSVP pass message, we have this information, explicit route. Here we need to see the ERO. Look at here, this is the ERO. And after that, the label request, and after that, the session attribute, after that, sender tunnel specification. It's okay. Also about the RSVP reserve message, we have this information. The label receive is 0. This means that we are sending the null, okay, or explicit or implicit null. Don't worry about this now. Let me to say the pop message or pop label. And after that, in the, for example, RSVP reserve message, we set the flow specification as the required bandwidth. It's okay. Now we can understand the process of the RSVP, but let me to remember that when we are sending a normal traffic, we are using the label forwarding. Label 200, it should change to 300. After that, for example, it should swap to the 401 and finally pop. We can see this process also starting from the router 1. In the router 1, In the show MPLS traffic engineering tunnels, we can see that we received the outgoing label of 200 on the fast Ethernet 00, and also in router 2, show MPLS forwarding table can show us that we need to swap the label 200 to 300, or if you want, show MPLS traffic